Now you speak.
In fact, connector only I have. Connector alone I have, but the power adapter.
Connector है.
Connector CTech connector, but USB C2 not C, this USB.
C to USB है ना? बस वो चाहिए. वो लेके आएंगे. हम घर लेके आएंगे.
Start right. So, good afternoon to all of you. Let us start the program now. So, before we start, our greetings to all of you who have come and participated in this particular program. Before we start this program, it's a pleasure to welcome the chief guest on this distinguished lecture with flower bouquet. And I invite Dr. Chancellor to open the bouquets. Right now, Dr. Kamachi Mudali. Thank you, Dr. Well, I was really not knowing what I should talk in this welcome address. Then I thought I should rather justify why this particular CorSciTech is required, how important it is. I have spent probably about 30, 35 years in corrosion. And people still ask, what is there to do a corrosion research now? This corrosion research is very important. Can we already really challenge this? If you look at the periodic table, I mean, we are not invented any new metals. All elements are already available. The thermodynamic properties are already known to us. Go to library, we have treatises of like electrochemical science for various kind of metals available. Just look at the bar books. What is there for us to do research? The point is, in fact, we have distinguished guest today, Professor Krishnan, who is working on thermodynamics. Of course, he's also working on the kinetics aspect of that. When you look at all these metals, especially those being used for engineering applications, thermodynamically they are unstable. They are deep to corrode. Then how is it we are going to use them? We use them because we need to understand the kinetics. The kinetics is nothing but the mechanisms. The mechanism is something is still missing. We are to understand them much in details. Why do you need to understand the mechanisms? Because the technology is really evolving. Gone were the days where you have transportation vehicles, which are much heavier and all. We talk about thinner and thinner sections. High strength steels. We no more use very normal micro steels. Talk about high strength steels, 1000 megapascals. We want to use advanced high strength steels. Similarly, for aluminum alloys of high strength. But it has started developing these kind of materials of higher performance mechanically. They are bound to promote more and more, fracture more and more. So the metallurgists, the material scientists, they never stop making new materials of high performances. But then they face the problem of social problems. Similarly, the technologists, new devices. Now we know about mobile phones, which are more powerful than the desktops we used a few years back. But in the life of these are very small. Why? Because we are miniaturizing them. And when you start miniaturizing them, the corrosion becomes much more problem. In fact, these mobiles won't last longer because of heat, because of electromigration that's taking place. So as the technology advances, I think there is a need for us to understand more and more concepts. And also talk about proactive management, prediction, and so on. That is possible only when you have mechanisms. You can't put a probe unless you know what it is. So there is an ever-growing interest in terms of understanding the processes, and that is for sure. Things are not very standard. When I look at the industry, I've been visiting it many number of times. The corrosion guys always talk about cementing. Coating, strength, inhibitor start cementing. What a difference. Why we should do that? The problem is that there are several factors that come to pieces. Again, your technologies, your issues, your problems that we are facing. For a simple example, people talk about bromades very cheap, very effective, environmental problem, phosphates. Now phosphates are being phased out because the environment issues the problem. In fact, Kamachi has chosen a very nice topic today to illustrate this kind of aspects of this. So the problem is that industries also have to have more reliable technologies, resources, BBC resources, for example. You can't use same technologies. Corrosion is only where high temperature, high pressure in waters. Same thing on optical fibers. So there is a growing need for us to understand more and more. So what is this then? The CorSciTech will do a small thing. We are all corrosion warriors. Like for example, assume that there's a train carrying people with a mission. All of them are same mission. Let's say a chain of 1,000 people in there, or interested in corrosion activities, submission, how to prevent them. I would say the CorSciTech is only one seat of that, taking part in the mission of corrosion. So that's really a small difference in terms of making them aware. When you talk about advancing corrosion awareness, so that's a small, smartest thing that we want to do in terms of corrosion control. Where did this corrosion? This CorSciTech came to the picture. It came to the picture because we conducted a conference of Asian Pacific Corrosion Control in 2016, 71 in India actually, very successful. In the case, also we had a core committee where Kamachi Mudali was a co-convener, Dane was another co-convener, myself was the convener, and Dr. Late Baldev was the chairperson. So that was the origin of this particular one, where we were able to place resources to form the CorSciTech. But these are not the whole people. There are a lot of people who are involved, including you see here, Supranik, Chaudhary, we have Honorary Chandra, a lot of people came from BRC. All these people that participated in making this successful. So we are able to do this. So the course committee, RMSC committee of MCC worked very well and we were able to make impact in terms of tentative resources. We want to use that for a better purpose. So this is what the origin of this particular CorSciTech. We want to have it as something which we be able to advance the awareness and then and also quantification. So with this brief introduction about CorSciTech, and now I would like to welcome all of you. We have with us now Dr. Kamachi Mudali, a distinguished Corrosion researcher in India, and we have this function. We have a chief guest, which is Dr. Professor N. Smadhan, the Zedal department for this particular program. So, with all this, I'd like to welcome my behalf and behalf of the organizing committee, all of you for this particular program here. So, with this small address, and now I like to invite Sir Vishwanathan to give the president's address, and then inaugurate or launch the CorSciTech program. Very brief introduction to Sir Vishwanathan. Most of you are aware of it. It's a well-known researcher and a distinguished teacher, I would say. And he's also working with technology and currently is the head of department. With a very brief introduction, now I invite Smadhan. Thank you very much.
Thank you, Professor Raja. So, Dr. Kamachi Mudali, Professor Raja, IIM members, students, and ladies and gentlemen. Yeah. So I'm very happy, this Corrosion Science and Technology under the aegis of IIM is being launched from this place, especially as Department of Metallurgical Engineering and Material Science. I'm very happy to do that for a simple reason. We have been one of the pioneers, or rather the pioneers, as far as education in corrosion science systems and science and technology, or science and engineering is concerned. As I understand, this is the only master's program in the country, corrosion science, that is from this department. And of course, we also have, related ones, for example, corrosion and quite often steel also go together. But there are also other metals which also part of corrosion, but steel comes again first. So we also are quite strong in steel also. We have a very program in steel technology also. So that way, it brings in a lot of synergy in terms of working on different topics and all those things. And I'm very happy that it is being launched from here at this department. And of course, if you look at the students who come out of the Dr. Kamachi Mudali himself is an alumni of this department. That is also, if you may not know that, so also from this department. So that's also a great pleasure. So many students who have studied corrosion from this department have been, leading many of these activities, not only within India, but abroad. That's what Professor Raja was also talking about. So with this, I'm very happy that this is happening. And so let me, as chief guest, as Professor Raja put it, let me say that we officially launch this corrosion science and technology. Right? That's what is under the aegis of Indian Institute. Thank you.
Yeah, Professor.
Any key?
Oh, okay.
Thank you.
Thank you very much.
Thank you, Professor. Now, I have daunting task of introducing the speaker to any of us. So whoever is remotely related to materials and corrosion science,
will be aware of Dr. Chancellor's achievements, but still for the sake of publication, I bring out some of his achievements. And Dr. Kamachi Mudali, he was superannuated from the Department of Atomic Energy as a distinguished scientist and as the chief executive and chairman of the Heavy Water Board. Currently, he is the vice chancellor of VIT Bhopal University and also an honorary professor of practice at IIT Madras. So, before superannuation at Heavy Water Board, he had many achievements. So, he made pioneering contributions towards non-nuclear applications of heavy water and oxygen rating for societal and healthcare, production of specialty materials, which is of interest for nuclear power plants and fuel cycle, and new initiatives for industrial production of DDW, that is deuterium depleted water, and rare metals, which is, we all know, very important for us. So during his stint in heavy water, he also achieved record production of heavy water in heavy water plants. There was a lot of heavy water plants in Hazira, Tuticorin, Madras, Baroda. So all of them, they have some landmark achievements under his leadership. So before moving to heavy water board, he was of course spent his majority of his career in the IGCAR, Indira Gandhi Center for Atomic Research, where he finally served as the group director of materials chemistry and metal fuel cycle. And, during his tenure in IGCAR, he had made similar contributions towards establishing high nitrogen stainless steels, synthetic high nitrogen stainless steels, various modern alloys like high integral alloys and bulk metallic gases and their applications in nitric acid development, and also coatings. He had some lot of work in coatings also. And also the failure analysis. He was actively involved in failure analysis, consultancy, corrosion, audit and survey of DA plants and other industries. So, and he's also recognized as the world's top 2% of the scientists from India in the field of materials, and has 468 journal publications, 22 books, 5 patents, 275 lectures, honorary lectures, and more than 10,000 citations for his publications. He is the chief editor of Journal of Electrochemical Society of India, editor-in-chief of IIM Springer book series, and CRAI Corrosion Management Committee booklet series. He is trustee of the board of ASM, International ASM, member of 12 professional associations, including 3 from abroad. So he has been also been, in recognition to his achievements, he has been bestowed with a lot of honors and awards. Prominent among them are the Metallurgist of the Year Award from the Government of India, Indian Institute of Metals, GB Builder Gold Medal and Platinum Medal from IIM, Tamil Nadu Scientist Award, Master National Award, Westwick Award, Indian Nuclear Society Medal, Distinguished Faculty Award from HBMI University, UNCTE IIT Distinguished Visiting Professorship, Honorary Science and Technology Award from DA, and many more. So it takes a lot of time to read out everything because it is so well recognized in his contributions. He has widely traveled all over the world, giving lectures and in different capacities. So with that, I invite Dr. Kamachi Mudali to deliver his first CorSciTech distinguished lecture.
Every week, huh? Good morning. Okay, yeah. So To get it, huh? Is that it?
Yes, sure.
Leaving. Expected. Senior from the Department of members of the Indian Capital, Mumbai chapter, students, for this first CorSciTech distinguished lecture. And extremely proud, actually as the former president of the Indian Capital, but also as the former student who studied in this department. 1982. It was a great opportunity at the time when I joined Corrosion Science and Technology. I was chosen campus interview to the reactor where research center at Alpha. And then the rest is history for me. Very proud to be coming back here. I was also honored by my alma mater in 2019 as the distinguished alumni. Very proud moment. I came for also the last degree qualification. I'm really overwhelmed. Thanks to Professor Raja, the CorSciTech distinguished lectures in hospitality, for choosing me to give this first lecture. It's a great honor for me. I think it is a great recognition to me and my colleagues who worked along with me. And of course, to the department from where I have come up to this level. I have chosen this title. I'm wondering that what I should talk either to focus on the researchers and some topic, currently, do something that is general, that can create knowledge, awareness to others. Then I saw the baby's series saying is to bring awareness about corrosion. I felt that I should talk about corrosion and its implication on sustainable development. All of you know that in the year 2015, the United Nations General Assembly passed a resolution that something called Agenda 2030. There is a slide I'm going to tell about that. In order to bring better living and better improvement in the sustainability of this world, they have identified some 17 goals. 17 goals that has to be undertaken by 154 member states. Every year they have to give and go to the United Nations and the General Assembly. This will be monitored till 2030. See that they are all implemented. So this is to see that there is going to be a complete sustainable development. Means the development is going to be for bringing better living, better better education, healthcare, food and water security, infrastructure, shelter for those people who do not have it. Everything is sustainable development.
We are all basically metallurgists, and all of us know that metals play a very important role in the studies of, I think, also in the development of civilization. And we are never worried about the resources. Plenty is available in the earth, Mother Earth is great, it's a resource of all the metals, whatever you name it, but you can get anything that you want. So you are liberally taking it and then you are using it. Just now, Professor Vishwanath mentioned about steel. Everybody thinks that steel is very cheap. Maybe its price is very low compared to all other prime metals. And steel will rust, but you can very easily paint it or coat it or whatever you can use it for every application. So steel is nothing that is, plenty available. You can take it and but I feel that steel may be a king of all the alloys that you make from iron. Steel is going to be a wonderful alloy that is going to live forever, make this sustainable development that will happen in the future. So we need to have the sustainability of iron. We need to have sustainability of certain metals, whatever is available, so that the future generation to have these metals available in order to have whatever that better living conditions for all the citizens in the world with sustainable. What is the corrosion is playing a role? You know that steel corrodes, everybody knows the 0.125 millimeter. Everybody wants to bring it down to 0.01 so that you can use it for a prolonged period. And steel and crust are like, you cannot separate them. It undergoes a lot of corrosion in the service. So, how this corrosion can be linked to sustainable development? What is the role of corrosion? Plus the theme that I have. So, being a corrosion specialist working for the last 4 decades, let me first say some basic because I know a lot of young students are here. Just motivate them. What is its relevance? How it is manifested? The manifestation is a very important thing. Like a disease, what people say that human body has several diseases. Corrosion also manifests as several diseases, and that's what is a very important thing. Second point that I will touch about the cost and economics, when people call it corrosionomics, because it is going to be 3 to 4%. That is what people say, but it is much more than that. 3 to 4% of GDP today for India is a very big number. How this corrosionomics can be understood, can be taken care. I will say a few strategies that what we should do for corrosion prevention and management. This is based on my experience. In general, particularly for the Indian scenario. Then I will try to link up the sustainable development and the material scenario, particularly what is the role of steel, the impact of steel, and its sustainability towards the sustainable development. And we also bring in the not only corrosion, in addition to corrosion, other sources of wastages of the metals and alloys, the scraps, the solid waste, e-waste, electrical and electronic waste. How all of them can be recycled to make the sustainability of metals. And then I will say something about the circular economy. It is very, very important today with respect to both the primary sources of all the metals and alloys and the secondary. And with the recommendation and procedure. The first question that comes into the mind of everybody who is not aware of that about metals and alloys, that except gold and platinum, all of you know that all of them will corrode in service. And steel is a beautiful example that just Finish polish it, keep it outside. Within seconds, minutes, you will see the first line is covered on the entire surface. If you look at the corrosion cycle, basically, you know that every metal is available as a mineral compound in the crust, mine it, excavate, 2 mineral beneficiation. Then we melt it, we do the grinding alloy, make metals, and then we make alloys, then fabricate them into various products that can be put into service in the industry. And there comes the role of corrosion, the service life of these components in service, where corrosion plays a major role, either due to an intended service of environment where there is a corrosive environment, or it is an external air, moisture, or environment that is there. Finally, corrosion becomes one of the major degradation mechanisms by the components prematurely fail and you lose the metal and rubber there. It becomes a waste, it becomes a scrap, and the cycle is not complete. Whatever the energy that we put in from ore to product, so entirely lost almost doing of the energy is a waste or a scrap or a product. What is very important here is that we should close this loop where we have to do reuse or sustainable development. Sustainability of these products are very important. That is why that I'm touching mostly on this corrosion, waste and scrap. How we can effectively close the loop that will give me back some of the minerals can be reduced in the primary source so that they are available for future generations. Same time, whatever I have produced with intense energy can be reused, remanufactured, can be redesigned and made into products. You go to any industry, basically you will see steel is everywhere. Not only that, you just look at this building, you will have plenty of steel that is available in your chair, in the building, in any component that is any instrument or any system that is present. It's always there. Particularly, you go to an industry, you will find 90% of the structural components made of steel. To avoid rusting, which is mandatory to happen on the steel surface, we do painting, we use coating, or we try to use better version of the steel that is stainless steel. This is what we try to manage steel for all the industrial applications. 90% is going to be steel. In my personal opinion, all metals and alloys, except gold and platinum, I consider them as a frozen thing. They are hungry. They are always trying to react with the environment. If it is iron, it reacts with oxygen. If it is copper, it reacts with sulfur. Silicon, it can react with carbon. So they all try to react with their own partner from whom they get separated during this whatever melting and way. And then they go from their metastable state to the stable state. This is what we see as a corrosion cycle. And corrosion is not so simple. It's not just metal that contributes to corrosion. There are so many factors. That is what makes corrosion a very interdisciplinary subject, which demands intervention of expertise from various other fields. Chemistry, from metallurgy, from physics, from civil engineering, chemical engineering. So that is where that people have some inhibition on the subject of corrosion, because you need to have multiple expertise, intervention of specialists in various domains, understanding of corrosion and controlling and prevention. That is happening. There are a number of things, particularly the status of the metal. We have a galvanic series, the active series to the noble length. So where it is light, that's very important. Then the nature of the environment, nature of the interface that forms between the metal and surface. Then we have the knowledge about the product that is forming, maybe some oxide steel, some product which is porous, which is continuous, all that. Then the environmental parameter like temperature and pressure, the pH, the oxidation or reducing ions at that percent. Even if it is an air, the relative humidity is very important. Below 40% R, the relative humidity, if you are able to maintain any equipment, component in atmosphere, you will have a sustained sense of the component without undergoing any degradation. So we have a steel component, we keep it at a very high humidity condition. it also naturally undergoes corrosion. So that is where that even a Mars air purity can also play a major role. For the betterment of the students, young students who are here, the corrosion is a very simple subject. We make it very complex. We think that there are so many chemicals are coming, cancer produced, so many things are happening just for rusting. If you will write some 10, 20 equations, get a lot of allergy for it. So many equations are brought in, Nernst equation, Butler-Waldner equation. So many things are brought in. As simple as that you put a small iron piece into dilute hydrochloric acid. Immediately in few seconds, it's seen on a box. Very simple reaction that is happening. What is happening? Iron reacts with hydrochloric acid, it produces iron chloride and hydrogen. I can split this into two simple reactions, like metal going into the valence, higher valence state in an ion state, releasing its valence. But is Fe, is Fe2 plus 2 electron, or Fe3 plus 3 electron, depending on the number of valence states. Aluminium, plus, niobium, 5 plus, titanium, 4 plus. You can think for any metal that you put into an acid. Acid contains a lot of hydrogen ions. These ions can get reduced by consuming this electron. When you put a metal simply dissolves into ion, releasing electron. The electron is just taken by the hydrogen to become a hydrogen. So Fe plus 2 H plus use Fe2 plus Fe2 plus reaction with Cl plus very simple reaction where this production of new electron and its reduction. This is going to determine rate of the any chemical reaction, you know that the rate determining step is the smoothest step. So here, the electron transferring from metal into the solution, then transferring to the other ion that is consuming, that is going to be the rate determining. Since the electron transfer is the rate determining step for electron chemical. Otherwise, it is simple chemical reaction. Put a lead in sulfuric acid, lead sulfate is formed. You can see in far back. There is this corrosion of iron in hydrochloric acid. The rate at which corrosion will take place depends on the rate at which the electron is produced and consumed. Same thing applicable for all the metals which corrode like this without forming either soluble or completely irradiated. We put aluminum, which forms alumina, put lead sulfate. The same thing we put iron in hydrochloric acid. Corrodes, it will not form iron oxide. So that is where corrosion becomes an electrochemical reaction with the transfer of the rate determining step. Understanding of corrosion, like Raja was telling that there are so many thermodynamic identical places into the equation. Today we all know very well that the advancement in science and technology. Every chemical reaction is controlled by the kinetic process. Thermodynamics can give you only the tendency for the corrosion. When I was studying, it was only the 4-by diagram that was considered as a great thing. The 4-by diagram will tell you iron, water, you have different zones, passivity zones, immediately zone, corrosion zone. Okay. So you will know that in this pH potential it will be corroding, in this potential pH it will be passivating, or it will be totally immune. The immunity region you can go for cathodic production, the passivation region you can develop for stainless steel or you can develop coating. The corrosion region you cannot do anything. This is what a simple thermodynamic approach to corrosion control or corrosion resolution or corrosion application. And there are many points, many severe people that are here. And those days corrosion was considered something like a weight gain. And we put this iron in hydrochloric acid after some time, the iron will disappear. Weight loss. Nothing is there. You take something, that is corrosion. Or you put the same iron into some furnace, heat treatment furnace, take it up, so that it's a thick scale forming with the weight gain. Corrosion is so simple. Just weight loss, weight gain. Why there is a total corrosion? That is what the understanding of this. Then came the chemical and electrochemical. What I have explained just now, the hydrogen moving the electron. The electron transfer is deciding the kinetic of the. So there are theories coming in chemical theories and as well as there are more interesting theories and models that developed. Then came very strong metallurgical and surface modification analysis, where the microstructural effect was given structure property. What is the microstructure? You take a stainless steel, there is a welding in your group, there is a delta thread coming. Second case, that will have a problem. Otherwise, you heat treat it, it is getting sensitized, it forms a chromium carbide in the grain boundary, and then it leads to chromium with. So it depends on the microstructural condition, depending on the surface layer. So if it is, you are doing a nitrogen ion implementation, it forms less than hundreds of angstrom. Very thin layer, but it gives the highest protection in a orthopedic through an orthopedic implant made of cells in human body. So depending on the surface, depending on the layer that is formed, the microstructure, the more and more chemical and metallurgical, the interdisciplinary theories are. Today, I think with the advent of all the coming to microscope, scanning tunneling microscope, scanning around we are more and more going into the nano dimension to understand the alloy dissolution theory, kinetics of alloy dissolution, same way that you can also understand the deposition starting from atomic time. So you can make nano layers, multi layers for all the electronic and many other using the principle. This is what happening with respect to understanding of the corrosion. But corrosion unless initiates at the surface, with every metal, whatever that you have made, they all there is a discontinuity at the top surface. You have a dangling balls, they're highly energetic, they're looking for interaction with the atmosphere. So you always have corrosion initiating at the top surface. There will be so many imperfections, some secondary precipitate will be there, grade level will be there, okay, dislocation that is cutting at the top surface. And you will have a lot of such kind of defects on the surface where corrosion can initiate. It can be at the grade boundary, it can be at the base boundary, it can be some inclusion, and secondary precipitate. All of them, even if you take a single crystal, there will be a lot of thin size, atoms of the surface, extra length. So whatever that is there will be a corrosion that can initiate. It's not only this surface heterogeneity, they also need suitably an environment that will accelerate the corrosion. It can be a neutral, an acidic, a base, or anything that atmospheric corrosion or it is an aqueous corrosion or a gaseous environment. Corrosion will initiate at the surface. Once it initiates, this is what the corrosion is, something that is happening on the surface. As anybody knows, corrosion as rusting. The rusting is uniform on the surface, you will see. The same thing, you take a stainless steel, there is nothing like rusting. You won't see anything, but one day you'll find the stainless steel is completely, getting into two pieces. That is because it can undergo stress corrosion gravity, maybe in a fluoride environment. People say that even in ambient conditions, this can change. So there are a lot of opportunities for the corrosion to manifest into different forms. That is where the types of corrosion that comes. Earlier, people know that there are 8 forms of corrosion. If you take the Autonomous Green or the Clay book, you will find 8 forms. 8 forms. Famous lectures that will be conducted. Today, the microbiologically influenced corrosion is the 9th form. It is industrially very highly relevant, and it is not kind of an environment that falls into whatever I told, the gaseous environment or aqueous solid environment like a liquid filter. The microorganisms, whether they are macro or micro, depending on their perennial attachment, depending on the conditions that they generate on the surface, they can lead to different type of corrosion. So the uniform corrosion is the one that is rusting, whereas the other type of corrosion, like the fitting corrosion, formation of a hole. The cleavage corrosion between two joints it can form. Then the intergranular corrosion, that is between the grain boundaries. Then the hydrogen embedded, all of you know that hydrogen is sensitive, very light, it can penetrate into wherever there are some cavities or defects are there in the metal matrix. The galvanic corrosion, the two dissimilar metals, one of the weak, one will undergo corrosion. And the erosion corrosion, there is a flow medium in there. And then you have a fretting corrosion, very low amplitude of the movement, very low frequency, like orthopedic hip joints in a human body fluid condition can undergo that kind of fretting damage. Such corrosion cracking, you must be all know very well. Raja is a very established person on that. So all these types of corrosion are like diseases that we have. Human being have. You have plenty of fluid. Like you can list down from 10, 15 list of diseases that a person can have. Sometimes a person has multiple diseases. So like that, if you go to an industry, you take a heat exchanger, it can undergo release corrosion, it can undergo burning corrosion, it can undergo heating corrosion, and there can be some corrosion which is propagating or some corrosion fitting can happen. So which one is going to be the fastest growing that will determine the life of this component. So there can be a premature corrosion failure based on any one of these type of. So it's not that today it is very difficult to isolate that particular type of single corrosion that contributes the corrosion failure. It is always multiplex of phenomena that will take place. So these types of corrosion lead to the corrosion growing the component and then damaging it. So what happens if the corrosion gas around 40 having it in the tank? This tank was overpressurized during the studies. There are two things. One is that the corporate mismanagement without any safety protocols. Second thing is the human error. People have just without following rules there and something. So that led to a runaway chemical engineering reaction because of the rusting that has happened, and the iron in the rust reacted with the methyl isocyanate and led to a chemical engineering reaction. That led to a huge explosion of the tank, and the entire gas 40 metric ton came out, and that led to 5 lakh people instantaneously getting affected in Bhopal. So you just imagine that simple corrosion, rusting, where iron oxide is produced, the iron is the oxide. In fact, it is the same thing. So what are the impacts? So if wherever there is corrosion is happening, there is going to be a kind of whether it is happening in an industry like Bhopal gas tragedy with the Indian plant, or it is in the public place. You can see a breeze or a water tap or a pump or a water pipeline, anything that is available, anything that you see in the public or in an industry, corrosion when it happens leading to failure, the impact is going to be very, very significant. The first one is economic. If it is a single component that failed in the service due to corrosion before its lifetime, then you will replace it. So there is a downtime and there is a replacement. Downtime will lead to production being reduced, and then the replacement will be additional cost to the plant. Okay, then if it is not to be replaced, then we have to do frequently maintenance. It will lead to some leaking. You close the leaking. For example, in a heat exchanger, the number of tubes. We have some 1,500 tubes titanium heat exchanger. Seawater is used as a coolant, and it also has a lot of microorganisms. So a tube phase, we close the tube and then continue to operate. We don't shut down the plant because the condenser is having one tube leaking. So, but how many tubes you can allow like that due to corrosion? Maybe some 40, 50, 100. But beyond that, what will happen? The cooling capacity of the process water is reduced. So that means the power that you can extract into it. So it will have an impact. So you cannot do frequent maintenance in a running plant, whether it is a chemical process or a power plant, any other. That's a safety impact. Loss of life, injury. Okay. So you have some small country where there is a steel boiler. You will read many times if the steel boiler is there, in almost every industry. It explodes due to some faulty welding and corrosion or many reasons. That leads loss of life, loss of injury, and you lose the best manpower, skilled manpower, trained manpower. So that leads a lot of. Then there will be a lot of legal and regulatory issues. Then the product impact. If there is corrosion happening, your product will be improved. In a pharmaceutical plant, there is everything is made of stainless steel. Even if there is going to be a corrosion that will happen 1 mils per year, that is 0.45 millimeter, that will lead to that much iron that is getting contaminated. So it is not allowed such, beyond the technical specification, the iron quantity can increase. Then the customer's dissatisfaction. If your product is going to be improved, having more, look at the chemical assay of a product, if there are many other elements, unwanted elements there, then the customer is not satisfied. Then also they will use the market, they will go to the competitor, the better products. Of course, finally, the societal impact, the public safety is affected in the Bhopal tragedy, the environment is getting damaged. So all these impacts, the corrosion in the industry and public lead to loss in economics. It costs so much to the corrosion, it has so much impact on the economy. In the year 2002, the United States Federal Highway Authority and the instruction from the Congress, they have done a corrosion cost that was around $76 billion of the United States. Recently, in 2011 to 12, the NACE International, the National Association of Architects, they have made a study that is called impact study, that is international measures of prevention, application, and economics of corrosion technologies. They made an impact study, and they have found that the worldwide direct cost is about $2.5 trillion, which is 3% the GDP of the industrialized countries. You can see here that the average is 3.4, and the United States on the top is about 2.7%. And you can see India is here about 4.2. And if you look at Japan, it's most advanced in corrosion control technology, which is 1%. So average is about 3.4%. And GDP of our country is 2.94 trillion in 2019. If I take 3.4% of that, is about $102 billion, which is roughly about 7.2 lakh more loss due to. This can be used for huge money that can be used for the state, at least 2 or 3 states' budget, annual budget in India. So that is the loss that we make, but it never gets an attention in this country. We think that corrosion is nothing to. This is what is happening. And out of this, 25 to 40% is a well-established procedure by which the cost can be reduced if we adopt the corrosion prevention and control technology. This is where the corrosion awareness is very, very important, and I am delighted that a series of lecture on corrosion awareness today is given by the Indian Institute of Metal Research. I am very happy about that. So if that let it happen, the corruption is happening now. How can I reduce this cost, and how can I simple method? There are different ways that one can do. The starting with the proper selection of material. Maybe the first choice is that you have chosen a common material. Okay. Second thing is that you should adopt best engineering practices. If you are fabricating, building, if you are doing any treatment to the metal component before putting it in the best engineering practice. And third one is that instead of the choice of the material and its fabrication procedure, you are using it to your Bhopal protection, cathodic protection, anodic protection. Okay. Then the next choice is that even if you are not able to control with that, you go for higher alloy, better alloy. Maybe the steel is not useful, you go for alloy steel. Alloy steel is not better, you go for stainless steel. Not good, you go for nickel alloy. You can go for titanium alloy, zirconium alloy, depending on the requirement. Then you can also, if it is something like the cooling water system. Almost every industry will have a cooling water system. The corrosion inhibition is very, very important. It looks like a routine thing, steel and water, combination. It's economic loss in the country. So corrosion inhibitors, protective metallic or protective organic. This is what This is what is the, the kind of toolkit that I would recommend that people can use for managing the corrosion and saving. Okay. But the problem is that we know all this, but how to apply all this? This is what is very important. That is where that you have to become a specialist who can do this. And to do that, to apply this toolkit, you need a lot of knowledge because corrosion, as I said, it's an interdisciplinary subject. You need electrochemistry, thermodynamics, information technology, modeling, metallurgy, and precise. Okay, you should have, subsequent, at least, adequate knowledge in all these aspects to understand and then apply it in a plant. If you simply say corrosion monitoring, if you look at the toolkit, corrosion monitoring has different methods. The analytical chemistry toolkit has different methods. Operational data will have different methods. And non-destructive testing is different. So, unless you have a complementary techniques that are being used for understanding a corrosion actually that is happening in the plant, and then using them to arrive at an optimal solution for the corrosion prevention, it is not possible to avoid corrosion. It is not possible. You cannot just monitor only the water parameter in the pipeline, then you can control the corrosion. Or you can just monitor the entity of the pipe, you can control the corrosion. It is not possible. It is an interdisciplinary approach that you have to do using the corrosion management. I want to stop the corrosion. So, what are the things I can do if I know the management tool? Number one that I should do is to put engineering practice, that I should choose the best material environmental combination based on the experience, based on the literature. Second thing, I should reduce whatever possible stresses during the application. If it is residual or if it is a kind of service stress. But one more thing is very important, that whenever you do any application, if you are using any code, any practice, any procedure, it has to be followed completely in the design, application, and operation. You should also have some protective measures, like painting, coating, plating, and surface modification, better material, improved material, and then you have to have an improved environment. You have to use some inhibitor, you have to use some quality control, you have to have some online injection of some certain species, chemical species. So, whether it is an engineering practice or a protective measure or a better material or a better environment, all this can stop corrosion, but ultimately that it cannot be 100% stopped. Because corrosion is a natural phenomenon, it will happen. We are only delaying it to, so that we can use at least 90% of its performance, 90% of its, not 100%. So, what are the preventive strategies in management and prevention control? And then we should, in the beginning itself, try to have the life prediction, life cycle, and performance assessment of the component, so that you anticipate after so many cycles of service or years of service or the application in the plant, what are all the problems that will come using envisage in advance, then you should take adequate prevention steps at the time. You should also have some innovative corrosion technology tools. Many of them, have to be established through research, development, and implementation. For example, some online corrosion monitoring tools, innovative tools, electrochemical noise, a new technique. Now, how we can utilize this electrochemical noise to understand the fundamental signature of current that is coming over. The electron release is nothing but the current. So how fine I can measure? This is like a signature of the initiation of the current. So all this can be done through the research. Then increase the awareness. That's very, very important. The management should be made aware that most of the time the failure that is happening, the root causes corrosion. We can control and prevent the corrosion and saving. Then we should also motivate the industry and academia that corrosion is not something like a hopeless thing. Corrosion can be controlled if it is properly understood and proper measures are being taken up. And not only that, the industry or the researchers and academia, the government should have some policies, regulations, and standards and management practices to increase the savings that will happen if we control the corrosion. In our country, so far, there is nothing happening with respect to the corrosion control, and that is one thing that the corrosion awareness and the corrosion mission, national corrosion mission or control that should be taken. finally, that there should be more and more education and training in corrosion control, which is required, and not only to those who are working in the field, but also to the top management who are the owners, chairman and MD, all of them should be aware of this. Very happy that IIT Bombay started MTech corrosion in 1982. No other IIT has started. This is the only IIT which is continuously, bringing this awareness, bringing, the mentoring and bringing up a lot of young talented people in the whole country. This is the only IIT that So what shall we do in our country? Suppose we want to have a sustainable development. Okay, sustainable development is that we have a better living condition for I told with respect to security, and water, infrastructure, healthcare, education, many things. So where is this going to manage this number? Corrosion has to be managed because we want to use all the metals and parts in a sustainable. The first thing is that the corrosion has to be accurately predicted for the country, and we have to establish a lot of new methodology for that. Second thing is that there should be a national corrosion mission. There are so many, energy missions. There are so many food and water missions. There are many energy, green energy missions. But we don't have something we never heard about national corrosion missions. And also something like the Bureau of Corrosion Control. Bureau of Energy Control is there. The energy efficiency monitor. Okay, so using some, the effective use of the power energy is always certified by the government agencies, and you are given some reward. So that we should have also such things for the corrosion control. And there should be established corrosion control guidelines, particularly targeted to the SMEs, which is not available. Even the bigger institutes, like Reliance, they don't have any corrosion, well-established control. And then the online monitoring is very important that we don't do in our country. We are not well established in that compared to Japan and USA and Germany. And we should have R&D thrust on new control methodologies to save in the economy, energy, and materials. And of course, finally, that we should have a lot of certification programs for corrosion. I would recommend that IIT Bombay should conduct also a lot of training programs, certification programs in corrosion, which will be highly, attractive for a lot of people, particularly the pipeline sector, which is, there is going to be more than 80,000 kilometer pipeline going to come in the next year. And several, the corrosion issues are there with respect to the transportation of various ingredients in the pipelines, including the future hydrogen gas. I think there are some kind of training, specialized training programs that we should happen. That is the corrosion I have told about it. Now I am going to cut it one of the deterrents for this. As I told, Agenda 2030 it was the 17 goals with 269 targets that identified by the United Nations Assembly in the year 2015 for a better and sustainable world by 2030. And out of this, you will find that at least 7 of them are directly related to the metals and alloys. Unless you have the sustainability for metals and alloys, you will not be able to have sustainability. All these metals and alloys required for this, particularly for these 7 sectors, we need to have the. So we have either the production of the metals and alloys from the minerals or from the scrap, and we go the products. As I said, either we dispose it as a waste, or it is undergoing corrosion, or that we have to go for recycling. Recycling is the way where we can go for the sustainable routes, where we can continue to use the metals in the alloys for a long period. And in this, the disposal, whatever that is going as a solid waste, the corrosion that is killing the components prematurely, or the waste like the electronic waste, all that is going to be recycled, then only we have a sustainability in the future. So just briefly, I would recap, then you have aluminium, then you have iron, then calcium, sodium, and so on. So iron is there in the 4th place. It's the 4th largest abundant that is available. And if you look at the parameter like In the year 2019, about 3 billion tons of iron ore was taken. 3 billion tons of iron ore have been taken globally. Okay. And out of this, 94% they utilized for only making iron and then steel. So you can see the way, the massive way the iron ore is being consumed by us, which is having some limited resource. And then it is being used, and it is about, the remaining 6% is only the other metals. 94% of the ore that is excavated, only iron ore. So, if, according to circular economy, the world consumes 100.6 billion tons of materials annually, and out of the 3.2 billion tons of metals produced in 2019, is accounting for only 3% of the overall materials. This is in a pictorial way. You can see this is the iron ore that we are, we are mining for producing steel and copper, aluminum, and so on. Then you have the precious metals, the noble metals, and so on. Of course, steel is the king of all materials, and as I have seen that 94% of the ore that is taken only used for making steel. It's a permanent metal used for all applications. 90% is the industry, non-biodegradable, 100% recyclable without loss of quality. But we don't do this recycling. This is where the sustainability is not getting. Sustainability is not met. So it is produced, basic furnace, basic oxygen furnace method, the electric arc furnace method, and we have about 3,500 grades of steel today existing worldwide. What is very important is there are 3 different ways in which the steel is produced. One is the secondary steel through the scrap in the electric arc furnace process, and this is the process where 30% of the steel is produced today. The other one is the primary steel production from the iron ore. That is the basic for the blast furnace and basic oxygen furnace process. That 70% is produced. That is where the more and more CO2 is coming into the picture, and we want to reduce this 70%, and then we want to increase this 30%. Where CO2 release is lesser, but it is energy intensive. If you look at here, you need 2.3 gigajoule of electricity required, whereas it is not that significant in the blast furnace technology, where you need more coal, you need less coal in the electric arc furnace. And one advantage is that in electric arc furnace process, you can use 100% scrap. And this is going to be the sustainable technology where entire scrap what you have and put into a electric arc furnace, and you can produce the steel. Today, India is the second largest. In 2018, we were number 2. And today, 2020, they produce about 21, it was about 120 metric ton. And government of India has made a steel policy in 2017, according to me. They want to increase its production from 120 billion metric ton to 300 billion metric ton production capacity by 2030. Means today, whatever the steel that is being consumed per person is going to be almost going to be double or triple. That is what is the objective of the government of India. And if you look at the world global crude steel production, China is the leader. Around 55% of the steel that is produced in the world is from China. And we are very limited. We are about 5%. You can see here, somewhere very small kind of India. And but we are the number 2. Our production today is 120 billion metric ton. China is 1,180 billion metric ton. So you can see the difference where it is. And that is the kind of steel production they make in China. And if you look at the world steel production and consumption over the year from 1950 to now, you can see starting with 189 billion metric ton. Today it has become 1,878 billion metric ton. Please convert this into iron ore that we have mined. Okay, so that is this is the kind of steel that is produced, and all this steel that is produced, whether they are structured, why we are keep on producing this, why we are keep on increasing this production? That's a big question. So if you look at the The overall productions in this is in 2020, you can see China because of the corona, there's a reduction 1,064 million metric ton, India at number 2 with 100 million metric ton. So the whole world is producing, USA is producing 72 million, Japan is producing 83 million metric ton, Russia is producing 71 million metric ton, almost the whole world. This is one particular entire world is producing without any break. And if you look at the per capita consumption, India is about 64.2 because in 2020, China is 691 kg. You can see the way, but the world average is something around 229 kg. So steel is being produced and consumed at a very high, very fast rate, and that means iron ore is being mined and then it is being used for various applications. If you look at the applications, today India is using maximum in consumption. India is now called IUC, India under consumption. So everything is under consumption. Anywhere we can go, there will be a lot of steel that is lying there, whether it is going to be used or it is already come for application. And there are a lot of applications in capital goods, automobile, and then the consumer goods, railways. Is going to be a big impact on the railways application, the railways. Except for this corona period of 2021, we have legally increased production. If you look at the compound annual growth rate, it is around, today it is around 6.5, and it is predicted that it will go to 7.2%. That is the rate at which we are producing. If you look at the total production of steel, 20% is only from the government, that is the sale, Steel Authority of India. Remaining 80% comes from all the private. You can see the production is actually in Jharkhand, you can see Odisha and Chhattisgarh. In Jharkhand, you have Tata Steel, Odisha, you have the Kalinga, their number of plants are there. Then you come to Chhattisgarh, you have JSPL, Jindal Steel Power Limited. In Karnataka, you have the Jindal Steel. So India is now the second in position because of the private people contributing so much to that. So when we produce more and more steel, not only that we worry about the iron ore that is required for future generation, but also the rate at which we produce the CO. The CO2 is something that we cannot decarbonize. If you look at the steel industry, iron steel industry, 6% of the CO2 that is produced only from steel. Apart from the other contributors, so actually maximum comes from the fossil fuel based power plants. Okay. And steel and iron steel plants give about 6%. That is the important thing. Now there is a target set by the Paris Agreement in 2015 that by 2050 we should go to net zero CO2. Recently, after Glasgow conference, they have now decided they have shifted the date to 2070 because it is impossible to make net zero CO2 by the time. And these are the various sectors by which CO2 today it is produced is roughly around 35 gigaton carbon dioxide per year. We want to bring it to zero by 2070. Okay. And if you look at here, 67% of it is around 67. I think gigaton per CO2 per year is from the steel plants. So iron steel industry is producing about 67% average CO2. China produces about 10 to 20%. India is producing about 8%. And 85% of the CO2 is coming from the primary steel making process. The blast furnace, basic oxygen technology, which uses heavily coal. For every ton of coal, we use about 750 kg of the carbon coal. And decarbonization. You also see, for example, the auto sector in this is about using 12% of the steel. If we can reduce the use of steel in automobile, more and more magnesium or aluminum and other parts, then we can also bring down the use of steel, and you can make available more iron for the future. But there are lots of innovative technologies that are coming to reduce the CO2. So the average, this is the average 1.83 to 2.21 ton CO2 released for every ton of the steel. Okay. The target is now to reduce 50% of CO2 produced during the primary steel making to the chemical reaction. All of you know that the iron ore reacts with the carbon, the heats the coke, and then it produces iron and then carbon dioxide. Second thing is to introduce hydrogen as a fuel. or at least to begin with mix hydrogen and then try to as a replacement to the coal and coke so that you will have lesser and lesser CO2 emission, at least by 20 to 30% you can reduce. The third thing is totally an innovative technology. That is what you can do is basically it is an iron oxide. So you can take some silicon dioxide and calcium oxide and make a melt 1600 degree, cause electricity, and you can do electrowinning. By which also from iron ore you can take the iron. That is going to be a breakthrough technology, but you have to use green electricity. Means the electricity that that's not going to use CO, coal or coke that will produce CO. So that means you have to have a solar PV based, energy that is coming, and then you do this electrowinning, then you will produce 100% you produce the green steel. There is already some 2,000 metric ton plant is there by I think ArcelorMittal company that is already there's a pilot plant that they are doing. So the government of India also considering that there is going to be 7.2% of the growth of steel demand. Their target is now the increase in the rural sector. The urban sector has seen so much steel application. They are going for higher steel production, and they are reducing the export duty. They are increasing so that we cannot import outside the iron ore, as well as import duty on steel items is enhanced, so that and also the import anti-dumping and safeguard duty, so that they will not do that. So the government of India wants the steel sector to grow multiple ways, so that our 64 or 70 kg per person will increase to at least 229 kg, which is the world average. We cannot go to 700 kg, which is Chinese per citizen consumption. The other important policy that we have introduced to use the scrap. So the globally that steel making, we have 600 million tons of scrap that is produced in the primary as well as in the secondary sector. So this is another important thing. Finally, if you look at the sustainable steel production, is possible only when you use the reusing of the byproduct gases, the furnaces, recapturing, cleaning, and reusing CO2 byproducts. Then the use of the electric arc furnace for steel production from 100% scrap steel using electric energy. Then use of energy intensive CO2 free fuels like hydrogen, and electrowinning is solar PV. This is going to produce green steel and make the steel sustainable for future. This also can be done through alloy design. You can have a better alloy which will not undergo corrosion and work for longer time. So variety of alloy steel can be produced, or with the advent of all the modern metallurgical characterization technique and the design concepts, one can always do an excellent alloy that will work for the entire period of the life that is being predicted. And that is also possible for other alloys like nickel alloys. Why I put this slide for nickel alloys? Next 20 years, it is projected that there will be more than 38,000 new aircrafts will be produced worldwide. 38,000 new aircrafts. Because the passenger transportation is increasing like anything. So this is going to be the number. That means that many nickel-based alloys, that means nickel-based alloys will be used that much. The titanium alloys will be required, steel will be required. Okay, so we are going to bring in more and more. Not only that, some critical metals are required. So there's not only steel, the other alloys are also going to do that. So recycling and recovery is going to be a very important concept for sustainable development. That's what I'm showing here. If you look at here, with the number of years of supply, the recovery, the recycle rate, one can use all these primary metals like iron, steel, aluminum, nickel, copper, all that we can use effectively, and the number of cycles will decide the recovery and then the energy that is required for that. And the most important thing is utilization of the scrap. I said that 600 million tons per year is produced today in 2020, and if we can use all this scrap back, then if you use the electric arc furnace with the intensity of energy from the green source, that will reduce the CO2 and make the steel more and more sustainable. Now, there are other sources Now, the most important I want to take is the solid metal waste, like the e-waste, electrical and electronic waste. The steel is very less. There are the other metals which are primarily required for the sustainable goal of the assembly. Very important. All of you know that e-waste is nothing. The electrical and electronic equipment, which is in a whole or as a part that is this product. Okay, the metallurgists have a great role to play in recovery of this, metal that is put into the waste, into this product now becoming a waste, and then reuse them. That's very important. Some of the critical metals are possible to be recovered from the e-waste, but it's a very highly complex because it's not a, like you take an iron ore, you get iron, okay, then you leave other things, as a waste. Whereas here, if you take a particularly a PCB board, there are so many components, there are so many metals that are associated. So you need some technology, some innovation by the metallurgists to, identify and isolate each and every metal so that finally you get back those metals. The energy supplied for this process will be much less than the primary metal production. India produces too much of, if you look at the first, the worldwide generation of e-waste, which is 53.6 million metric tons per annum, which costs about $57 million. And it is quite increasing in the last 5 years, 20% increasing. And it is expected that by 2020 to be 74 million metric tons. And the estimated value of recoverable material after processing is 25 million metric tons. If you process this 53 million metric tons, 25 million metric tons per annum we can recover from that can be reused, remanufactured into products. But what we are doing today in the world scenario is only 9.3 million metric tons, 17.4% only is getting collected and recycled. We are losing too much into the landfills and then scrap yards and waste. And India is world's third largest. Of course, China is the number one in the production of that. And if you look at the Indian scenario, in 2019, India produced about 3.2 billion metric tons. We don't have much technology in the industry level. We have only in the pilot plant level. It is going to increase heavily with the years. And due to the pandemic induced consumption of the electronic waste, it has been estimated 43% of e-waste has been generated in our country. You can just imagine. So it is going to be too much, particularly you see the waste that is coming from mobile and computer is going to be 1,800%, 500% by 2020. This is what is the assumption made. Of course, Mumbai is the number one in India producing these e-waste. And it comes from computer equipment, any equipment, medical equipment, electrical equipment, telecommunication equipment, not only from government, public and private, but also from households and from manufacturing sectors. So we are only, processing only 1.5% of this e-waste, and we have only 300 registered recyclers with a capacity of 7 lakhs only. Whereas our production of e-waste is 32 lakhs. We have only capacity for 7 lakhs. And in 2016, we only processed 4 lakhs. So that is the situation. There are some smaller vendors, small industries are there. The government is trying to support the R&D or recovery of this. And this is called the world's capital, Moradabad. In Uttar Pradesh, the world's capital of the e-waste by unorganized sector. Like, there are a lot of things within clandestine manner. They are collected there. It has been used for just extracting everything directly, burning the PCP. They are trying to collect gold because PCP has got quite a good amount of gold, so they try to get gold only. Then they get a lot of money out of that. And this e-waste has no limitation. It has been estimated there are 69 elements in the periodic table as an electrical and electronic waste. They are used in different forms in gold, silver, palladium, rare metal elements. Most of these are present here. This is gram per unit. Each mobile phone, you can see how much it will be. There you can find out from this smartphone. You can see that how much is there. And similarly, the electrical equipment also have the major elements like iron, aluminum, copper, and so on. Particularly, if you take the PCB board has the 25 to 30% the major elements like copper. You get a huge amount of the gold. You can see that 320 tons of gold it is 11% of world gold production and 7.5%, 7.5 ton of silver that is annually produced is available in this waste. And these are all estimation, 25%, 1/4 of the copper production, we are getting it in the e-waste. And 22% of the mercury is used in the electronic industry. So this is not getting, recovered. This is also useful. If we can take this, then we can keep the remaining the ores for the future generation and make these metals sustainable in the world. So most important is that as the electronic market is keep on increasing in our country, the way we can recover more and more monetary value of these metals are going to be very high. And it is estimated in 2019 that India is able to extract in 2018-19, India has extracted gold worth of 1 billion from the urban mining, this e-waste. So that is where that many unorganized sectors are there. But recovery of all these metals are very important because the urban mining, which is called now the whatever that is the e-waste that you process, the secondary processing, will have a reduced energy requirement. It avoids pollution, avoids the greenhouse gas emissions, and saves also natural resources. The recycling of iron, aluminum, and copper will contribute to about 15 million metric ton of the carbon dioxide that is produced otherwise the primary resources. And not only that, if you can refurbish this electronic equipment, electrical equipment, many people who are not affordable will have an opportunity to use them. What do you think that is a waste you discard it in the shop can be reused by some people? And finally, that it can do a lot of jobs. There is going to be a e-waste processing industry that is going to set up in the country to recover these metals to make it sustainable. And you can see here a statistic which says that 4.0 lakh direct jobs and another 1.8 lakh indirectly can be generated. So I am coming to the last part of my lecture that where I feel that the secondary resources like this e-waste, suppose we take this 54 billion metric ton at a per capita of 7.3 kg per person in the world. Okay, if we can process and we can remove the valuable metals, it will be about 25 million metric ton. Suppose we want to produce the same equipment that is about 53.6 billion tons, you need to only have 14 million virgin, and this 25 you can add to become 39 million metric ton. That's because of the technology advance and micro and nano fabrication. The same equipment which was made with 53.6 million metric ton can be made with 39 million metric ton. By recovering this 25 million metric ton from this e-waste, and then only adding 14 million metric ton. That means we are going to use less and less primary resource. We are going to recycle this. This is what is the circular economy that is going to make the materials demand in a sustainable way. Same thing can be done in the primary resources. Suppose we produce so many metals, iron, aluminum, titanium, magnesium. We only take the iron, but we don't take the the other elements that are present, the other byproducts that are coming to the the industry. If we can utilize everything, then it is also going to help in the the reducing the pollution, reusing these metals for various applications, and it will be most important for the conservation of the materials, energy reduction, and so on. So that is what is the thing that. So the last but not my summary for the way forward is that corrosion is something that is dangerous, that has to be controlled and prevented. Utilize in a better way, sustainable way, the metals and alloys in the industry. It needs to be, very important that we have to do the life cycle assessment, the risk management strategies for all the components. Whenever you are doing installation sort application in the industry, that will help us to enhance the utilization in an effective manner. There should be a national corrosion mission and bureau of corrosion control by the government of India. Also, government should establish well laid out the policies and the principles that can encourage the industry to adopt the corrosion prevention technology to benefit. And corrosion awareness, certification and training, skill of corrosion management strategies have to be involved for all the sectors including the SME sectors. We should have large, the R&D that is coming with very good funding and investment, not only from the government, but also from the private sector for new corrosion resistant material, process and technology, developing waste processing and recycling technologies on a long-term basis. So this is where the corrosionomics can be, can be updated, and there we can have an opportunity to implement with priority in the country. As a closing remark, I will tell that sustainability of metal is possible to have control of corrosion processes and also extending the useful life of the component in the service. That is where the corrosion technology play a very good role. And second thing is that there should be a long-term strategy with a white paper on material resources today available. The reserves. The resource is something that is what is the unpredicted amount of the mineral that is available. Reserve is something that can be mined, that is identified, which can be mined from that area that much. It's all, we don't have all this information. That should be, there should be a white paper and how much is the material requirement for features for various applications and their life assessment and management for the complete service or for the next 100 years should be made. The US is a treasure of valuable and critical materials for India and it provides open made of opportunities to urban mining. Very important that has to be done. Scrap utilization, recycling would also be enhanced in the manufacturing of these products to limit the favoring materials and to attain a circular economy. Very, very important. So this is what is today we will pursue: reuse, reduce, and recycle. This is required because all of us are thinking that we have this, inherited this earth from our ancestors. So we are retaining. Actually, it is wrong. We have borrowed it from our children. Okay, they are waiting for the minerals. We are waiting for whatever the resources that are available for their survival and their grandchildren. We should not think that we have got it from our ancestors. We have right to enjoy the whole thing, and we live in an unsustainable system, and there cannot be a sustainable development without sustainability of metals and alloys. And that is what my closing remark. Thank you very much for honoring me in this.
Thank you, sir. So we have some questions online that has come. There's one question from Raman Shankar Narayanan S from Trichy. So his question is, where do we, it's like India, stand in terms of hydrogen production?
Hydrogen production.
Hydrogen production. Where do we stand in terms of hydrogen?
See, there are different types of hydrogen. All of you know what we are interested in green hydrogen production. And of course, the fertilizer industries, they have source of hydrogen that is not for the green hydrogen purpose. And there are technologies which are very efficient technologies. Countries also creating them. Departments like our atomic energy department and ONGC, many other departments. As on date, we don't have any plant that is producing hydrogen that can be used for any larger applications. And it is not only production, storage of hydrogen, as well as transportation is the biggest issue because we cannot use steam. Know that hydrogen can increase the steam, or even develop some sporting technology that can be used for storing, such a light gas which can easily escape. Then transporting it to different sources and using them, and safety related issues. So and as I am aware that there is no huge production of green hydrogen.
There was another question. Do you expect India to become a leading world-scale commercial player for turbine materials?
Turbine material is basically a steel material, and today I think that only DHL is taking the role to make turbines in our country, and they employ people from the Indian steel industry. And I think only for the indigenous power plants, the fossil gas power plants, as well as wherever DHL was exporting their power plant components, they're using it. This is what I am aware.
So any other questions for the audience present here? You can.
Sir, I want to know, since you are part of Niti Aayog, in e-waste thing, what are the technologies available commercially suitable to us? There any technology developed or it is under development?
No, we have developed technologies. Let me tell you, the National Metallurgical Lab is the leading player. Of course, many other CSIR labs like IFMT, CECR is Karakhadi. Department of Atomic Energy also has done very good technology for recovery of some of the very strategic and critical.
For example, lithium and lithium, they are commercially available now.
Yeah, combustion available. For example, you want to do from the PCP, you want to extract gold. There is a technology transfer possible from NML Johnson. Yes.
So one more question is from online. There's another question online from Dr. Hidayat. So how soon we can expect practical application of high entropy alloys?
Yeah, see, high entropy alloy is, just let me say from 2020 years, not more than 20 years of its now. And most of the R&D, most of the research today, if you take only going on the evolution of the high entropy alloys. Application wise, such a multi-component system has not been possible because there is more and more areas modeling on how we can have a better mixing of the various components to get a better alloy for a prolonged serving. Excellent property. That is what is now going on. Of course, during my tenure at IGCA, we have an alloy casting system where we produce legal-based high-entropy alloys. And we are trying to see some applications in nitric acid environment because nitric acid is employed in the spent nuclear reprocessing plants. And we have also produced significant varieties of bulk metallic losses. We have a very good program in the last 10 years to utilize them for corrosive income.
Thank you. Okay. Well, it's a very, very lucid presentation encompassing a gamut of things that covers the kind of corrosion effects in terms of how resources are being wasted because, and also the strategy in terms of recovering the waste metals. So thanks for the very nice presentation. My questions are of two kinds. One is that in US, there is a Congress and the NACE interaction, right? NACE, the professional society, interacts with the US Congress. The policies are being shaped. Now, you have also had several roles in terms of being the president of the IAM Institute of Metals. And how much the professional societies in India could be able to influence or interact in terms of molding the policies of the government? This is one first comment. So, what kind of things is, if you can share some light on it. The second one is, now we talk about a lot of, e-waste, for example. Are there any kind of focused policies in terms of improving the technologies of the, how do you, for example, the e-waste, we talk about urban mining. Are there considered policies, programs, coordinating at national levels, so that the technology can be not only developed, but can be more efficient? So what kind of roles are being played by the government? This kind of thing, yeah.
Thank you, Mr. Raja. The first one is that you mentioned about the role of the electrical society on the government policy. Let me tell you that India is the better, the very close relationship this year achieved ever for the last 20 years. National Metals State Award scheme. And during my tenure, I will tell you, 2019-20, when I was the president, Honorary Mr. this scheme. And in fact, he asked me to prepare some note or white paper, something on some clear position. We prepared, we deliberated in our council, and one is the major thing that has not happened is that why do we have a Ministry of Steel only, and then we have a Ministry of Mines. The Ministry of Mines handles all non-ferrous, copper, aluminum, there. And Ministry of Steel is only steel, same and that. Why can't we manage something called Ministry of Metals? So that all policy related to metals can be made at one go, with respect to the export duty or import. And that time there was a lot of discussion about the trade agreement with the Southeast Asian countries. Government has to have some kind of an agreement. And if you sign the agreement, there the Southeast Asian countries have the right to directly bring their product, rather than now they are supplying only some wire and the materialistic product, whereas they can directly bring the utilize the products that can be made out of these. That's it. There were a lot of discussion going on at the time that there should be a common policy, whether it is steel or whether it is copper or whether it is brass or whatever it is. There should be one defined department. So he asked us to prepare a document, and we have to prepare it. The second thing is that he wanted to have a kind of a national apex body on metals and materials. To set up one R&D lab, national R&D lab at IFMT, which will look into various issues like hydrogenism, decarbonization, the latest issue, green steel production. So we should have that. We have prepared that also. And then we are also involved actively in the national every year the secretary and the minister, they all come and we have a close relationship, and maybe that some of the produce certain document and give or white paper cannot be implemented immediately. Some of them may be likely to be taken care of later. But the major things, like Ministry of Metals, we have a close relationship, and we can always prepare documents. Right now, I think there is a committee formed under my leadership, circular economy and sustainability. We are supposed to prepare a white paper, submit it to the principal scientific advisor. This committee has been formed recently in the last commission. That was the first thing. Second thing, coming to the e-waste, let me tell you, 2017, there was a national committee formed by Vijay Yadav, by Dr. Saraswat, e-waste utilization. Recently, the e-waste. I was the chair, director of SECRI and director of CCRI and many other industry also took it. In 2019, we submitted full documents, document on e-waste management. And this was presented to Vijay Vice Chairman. And the proposal was that to begin with 5 industrial e-waste eco parks at the industrial corridors in the country, 5 different locations, with a PPP model, public-private partnership model, where the central government will give the license, give the support of 50% of the cost or something. The state government, where it is located, will give the land and facilities. And this is costing about, I think, to the government around 285 crores for this 5 co-parks. And this will be managed by Navy. And this proposal was put up to the finance department. Unfortunately, this pandemic situation started in March, and all these new projects have been put on hold because no resources can be used for new project. It's very much stop. Even today that is live, and I have no doubt that this government will certainly implement. Maybe I was told that the latest information that at least they are going to start 2 industrial eco parks, e-cycle eco parks, where right from the collection to the final product will be done. They collect it, they sticker it, and then they will separate it mechanically. Then they will take it to chemical plant, biomedical plant, or they, they will get the product, and then finally they will make it into useful form that can be taken for primary. So the entire ecosystem and part will come. If 1 or 2 will come, I'm sure it will happen. Delhi government has already made an announcement just 2 months before a similar report.
Thank you.
Nice talk. So, see, you talked about carbon reduction.
Yeah.
So, because we know that, as you mentioned, a lot of our domestic coal is used for carbon reduction. And most of our metallurgical coal we are importing. So, is there a roadmap? The country, how we want to decarbonize? Means, is there some kind of a roadmap for how we go to it? Because on one hand, we talk about hydrogen. Unless we produce hydrogen from sustainable sources, it is not going to, we are not going to decarbonize because we will produce hydrogen using carbon. That will be much more than if you straight away use the carbon in the process. So, do we have some kind of a plan from the whole country?
No, there are some high-level committees working on that. I am very well aware, particularly for hydrogen and decarbonization. Both they have it because I think our Honorable Prime Minister has promised that in not only in 2015 conference, but also the recent Glasgow conference, that there will be significant reduction in CO2 from the fossil fuel-based power sources. And he also promised to enhance the solar, that there will be less CO2 production. I'm aware of a high-level committee that is working on decarbonization of the entire country. That is there. I don't know whether they have brought out any roadmap or something. But otherwise, independently, there are many other like Tiki, theory, energy institute, and many of them are working on. And there are many individual players, companies working on it. For example, for hydrogen, the private players are doing a very good jobs. Those Adani, Reliance, they are going to set up. It has been promised that they will be the cheapest hydrogen in the world. Both government, I think, private, both are working together.
Just coming to corrosion problems. As you know, even though awareness is given to a lot of industries, most of them start the product with a low investment, with a minimum thing so that the plant can start running, and they run into a maintenance problems later. So what I feel from the IM and the government policies, like what we have done for the automobile sector, where the PSS has come, the safety issues and regulatory authorities give the permission to start the plant after all the material safety issues. So can we come with a proposal that if a plant is of that particular value, like 200 crores or 500 crores, the condition-based monitoring should be mandatory. Like nowadays, the presently a lot of sensors are available to detect the cracks, fatigue cracks, or corrosion cracks, or the corrosion occurring at different locations. Can it be just mandatory for a given sector? With that only, the permission will be given. So that we will be on par with the other developed countries like Japan and other things. It will lead to a lot of improvement in the losses due to corrosion. Then such a policy can be implemented through government and IM and the Ministry of Industries. Is a viability is there? Not possible.
Yes, see, I remember in 2015 we have submitted a document to the Ministry of Chemical and Petrochemicals, EC. And Mr. Something was the secretary. One is to have something like a Bureau of Energy Efficiency, BE. What BE does is they go to the industry, they audit and certify how much energy reduction they have done over the period. And you have some credit for that. similar kind of analytics can be given to people who implement the corrosion prevention strategy, condition monitoring, or inspection, preventive maintenance, whatever they are doing. So towards that, we made a proposal, and that was like a National Bureau of Corrosion. Okay, so where all these policies, if you implement this, you will get this credit, like that. This is what we have done that, and that was taken by the government at the time in the chemical policy, national chemical policy, but it has not come up because later on government decided that there is no more and more new societies and new commissions and new things. They don't want to start within the existing system. If such can be done, so that is what they are looking for. So they said that whether any industry, major industry, can take this as a so I think that it will come. It will come. It should be there. But I want to tell you one thing. In 2002, after the corruption control in USA, it was $276 billion. And then they went to the Congress, that can be given input tax credit. Somebody is simply okay, but that was not taken forward. In USA, it was not taken forward.
Okay, thank you, sir. So we need to close now. So thank you. We had a very lively session. Thank you again. So let's give a big round of applause.
The technical thing I just thank you for getting so many languages. Is it that whenever you have visited those things you are taking?
No, not like that. It's available with open source.
So thank you very much. So I request Mr. Vishwanath. What is it? Yes, fine, but it's coming from this video fix.
Yeah, that's right. Absolutely. That's right.
Yes.
Thank you. Thank you. Yeah. Just two more announcements. Just if you can just wait. Yeah.
So thank you very much. Thank everybody for attending this meeting physically and online. Making this success. I thank Professor Vishwanath, distinguished speaker, and I thank all our colleagues from the department, VARC, students, and also our audience online, joined online, for making this a grand success. Also, thank our support staff, as well as our technical staff. Grand success. And so that's all. So before I disperse, so there is one announcement from the ASM. Wait for the announcement.
We can announce later.
काम नहीं कर रहा, उससे बैटरी डाउन चाबी
No
like
problem.
it.
No problem.
On a road like that.
On behalf of ASM, I'd like to felicitate our trustee, ASM International, Kamachi Mudali.
Yes, whether it is a gold or something.
Urban mining code. Can be so possible.
Thank you, sir, for providing the opportunity.
Thank you.
I have one announcement. As the ASM International India chapter is organizing one mega event in November, 2nd, 3rd, and 4th. That is Madras Engineering Technology and Heat Treatment Show. And along with the exhibition, we'll have a lot of innovation pavilion, poster competition, and so many other activities related to our metallurgy field. So I invite all of you and those who can contribute the paper, delegate as an innovation presenter. So all are welcome. And if any need be there, Professor Raja will.
Professor Raja is there, Dr. Kamachi is also there in that opportunity. Dr. Prateek is there, all the people are there who are present here, I think they're all the part of that one. So please be the part of physically as well as whatever the way you can contribute. That could be very kind of you all. Thank you very much.
Thank you.
Thank you. Well, thank you all. I think please join for the high tea on the side.
Stop the meeting.
Yeah.
Thank you. Okay, I've taken a lot of time. The place has been.
Yes, sir.